Hi everyone, my name is Angel, and in this video I'll be explaining one of the oldest and simplest methods of encryption, the Caesar cipher. This cipher gets its name from Julius Caesar, who used it over 2,000 years ago to send secret military messages. The idea behind it is simple but brilliant. You take each letter in the message and shift it by a certain number of places in the alphabet. For example, if the shift is 3, the letter A becomes D, B becomes E, and so on. Even though this cipher is ancient, it's one of the first recorded examples of encrypting information, and it laid the foundation for the modern cryptography that keeps our data safe today. Before we dive into the code, let's talk about what encryption and decryption actually mean. Encryption is the process of turning readable text, which we call plain text, into unreadable form called ciphertext. Decryption does the exact opposite. It converts the ciphertext back into the original readable message using the same key or shift value. Let's use an example. If our plain text is "Hello world," and we use a shift of 3, each letter moves forward 3 spots in the alphabet. So that gives us something like KHOORZRUOG. That's our encrypted text. If we want to decrypt it, we need to shift the letters backwards by 3, which would return the same plain text of "Hello world." My name is Angel, and today I'm going to help you understand how encryption and decryption work using one of the oldest and simplest methods, the Caesar cipher. By the end, I'll show how a short piece of code can turn a normal message into something unreadable to anyone without the key. Every encryption process uses a key. It's a piece of information that tells the system how to scramble or unscramble the data. In the Caesar cipher, the key is simply the number of shifts. So now that we understand what encryption is, let's talk about decryption. Encryption is all about transforming readable information into something unreadable, the ciphertext. The goal is to protect the message from anyone who doesn't have the secret key. Decryption is the reverse process. It takes the unreadable ciphertext and turns it back into the original message using the same key. So basically, encryption hides the message, decryption reveals it. That's like me sending you a locked box. Encrypting it is me locking the box before sending it, and decrypting it is you unlocking it with the exact same key. The Caesar cipher is one of the oldest examples of this process. When Julius Caesar wanted to send messages to his generals, he would shift each letter of his message by a certain number of positions in the alphabet, the encryption part. So to decrypt the message, his generals would simply shift the letters back by the exact same number in order to return it to the original text. So one thing to notice is that the same key is used for both encryption and decryption, making the Caesar cipher a symmetric encryption algorithm. Most modern systems use the same idea, but with much complex ideas. Before we go over the code, let's go through a little background check. Julius Caesar's cipher was revolutionary in its time, but by today's standards, it's not very secure at all. That's because the Caesar cipher only has 25 possible keys, which means that anyone could try every possibility shift until the message makes sense. This method is known as a brute force attack. Another way to break it is through frequency analysis, which looks at how often certain letters appear. In English, for example, the letter E appears more often than any other letter. So, if a certain letter shows up more frequently in the ciphertext, it's probably a good hint that it represents the letter E. These weaknesses show why modern encryption is much more advanced, using larger keys, randomization, and multiple mathematical layers to protect our data. So now that we understand how encryption and decryption work in theory, let's see how this cipher looks in action. We start by including the IO, stream, and string libraries. These allow us to use input and output commands and handle the text easily. Next, we have the encrypt function, which takes two inputs, a text string and a shift value. Inside the loop, we go through each character in the message. If the character is a letter, we shift it forward in the alphabet by the number given in the value. This next line ensures that uppercase and lowercase letters are handled correctly and that the alphabet wraps around when it reaches Z. For example, if we shift Z by 1, it becomes A, and if the character is like a punctuation mark, we just add it as it is. In the next part of the code, we have the decrypt function, which looks almost the same, but instead of shifting forward, we shift to backward by the same number. To do that easily, we just call the encrypt function again, but replace the shift value with 26 minus shift. This reverses the encryption process and gives us back the original text. In the main function, we ask the user to type a message and enter a shift value between 1 and 25. Then we call the encrypt and decrypt functions and display all three versions of the text: the original, the encrypted, and the decrypted. So to wrap everything up, let's take a moment to reflect on what we've learned. The Caesar cipher might seem simple, but it's incredibly important because it represents the starting point of data security. What Julius Caesar created over 2,000 years ago wasn't just a secret code. It was the foundation of how humans first started thinking about protecting information. In this project, we saw how a basic mathematical shift, something as small as adding or subtracting numbers, can completely transform a readable message into something that looks like gibberish. That's the essence of encryption: taking information that makes sense and transforming it so that only someone with the right key can understand it again. Through our C++ program, we saw how this process works step by step, using loops, ASCII values, and modular arithmetic to encrypt and decrypt text. Even though it's simple, the logic behind this code connects directly to how modern algorithms work. Today's encryption systems, like AES, RSA, and SHA, still rely on mathematical transformations, just on a much larger and more complex scale. The Caesar cipher also reminds us the balance between security and simplicity. While this cipher can be cracked in seconds today, the idea behind it, hiding information in plain sight, remains at the heart of every cybersecurity system we use. When you think about how this tiny algorithm evolved in protecting billions of people's passwords, bank accounts, and even government's data, it's pretty amazing. So even though this project focuses on a simple cipher, it gives us a hands-on understanding of something much bigger: the world of cryptography and how important it is to keep our information private and secure in the digital age. Thank you for watching, and I hope this helped you not only understand how the Caesar cipher works, but also appreciate how such a small idea grew into one of the most essential fields in computer science today.